for this summer. My name is Guillermo Avendano Franco, and this is a workshop a little much more specialized compared with yesterday. For those who attend yesterday, yesterday's more introductory, is more broad in the scope. This one is more targeted to GPUs, and the reason why we are offering this workshop this summer, is because we just received our newest cluster, which is specialized for GPU computing. So we will introduce a little bit what we can expect or not from these kind of systems from GPUs. So let's get started. How many people we have right now? 18. Okay, not bad. We have like 40 people registering, 40, I think, a little bit more than 40 people registered for this session. So we have half of the people. I think that a few will enter in the next few minutes, but for all of you, we're starting right now. So let's review a little bit the scope, what we will be covering in these 2 days, in those 2 sessions, today and next week. So we split this workshop in 2 sessions, 2 hours each. So today I will explain a little bit generalities about GPUs, what they are, what they do, a very generalist view from that. After that, I will hope to explain a little bit what are the different paradigms of parallel computing. So in computers today, you have a variety of things. You have multiple CPUs with multiple cores. This is one thing. And also we have one or more GPUs on a single machine that are also capable of some parallelization or some parallel computing. So how you mix all that, how you use that. And also you have the way in an HPC cluster to have multiple machines that can work together on a single problem. So that is another level of parallelization. So understand all that is what is called hybrid parallel computing. So, and GPUs play an important role in all that. So we will put that in perspective. This is not a course for developers, but still I include a little bit just to give you the flavor of what it is, how you program GPUs at low level. So I will show a brief pieces of code about CUDA, which is the lowest level that you can achieve for programming, at least NVIDIA GPUs. All the NVIDIA GPUs are not the only GPUs available. There are some others in something what is called accelerators, in the range of accelerators. But the NVIDIA GPUs are very popular. So CUDA is a tool developed for programming this particular kind of GPUs. And I will introduce deep learning and how you can execute in different ways deep learning and training or applications on a cluster like our clusters. So in particular, we will use Torney, but this applies when we officially activate Dolly sounds for production. And in the next session, we will be, next day will be for next week, classical molecular dynamics, which is another big reason why people uses GPUs today, and other applications such as computational fluid dynamics and general applications in where GPUs can give you an edge on that. So for those of you who attend this, I think most of you attend yesterday from what I saw in the registration list. But still, I will introduce a little bit how you can connect to our clusters more briefly, so you can read here what it is. there are basically two ways to connect to an HPC cluster like ours. One is SSH, an SSH client, and depending on which operating system you have, there are different clients available. So if you are using Windows, you probably need to install something like PuTTY or Mobile Extreme. So an SSH client, those are not the only ones, but those are two applications that you can download and compress, and there is a tiny application that you can execute to connect to the cluster, and the instructions are right here. So I have a few screenshots that guide you a little bit on what you have to do, and there is a generic explanation of what you have to do to connect to Thornflat. And so there is a two-step process in connecting into that machine. In the case of a Mac, it's simpler. A terminal, they already have an SSH client, so you can connect directly with that. On a Linux machine, it's pretty much the same. You open a terminal and you just type the command for connecting to the gateway, and from the gateway you connect to the cluster. And the other way, so that we will be exploring at least today, we will be using this, is Open on Demand. In Open on Demand, you can create a Jupyter notebook, and the Jupyter notebook could have, for example, for the deep learning, one of the 3, 4, so we support the 3 major Western side deep learning engines, which are TensorFlow, PyTorch, and MXNet. And we also have another image for supporting the eastern side, Paddle, which is a popular Chinese deep learning engine. So we have all that. So here we have the instruction on how you connect to the cluster. But let's focus on GPUs, so you can read this, how you connect to the cluster, and let's move on to our first session here. Okay. So, starting around 2000s, most computers start having multiple cores. So before that, one computer or a normal computer had just one CPU, and that CPU has just one core. So if you just need more power, you just buy another processor, which typically double the speed, the clock speed of the processor, so that give you roughly double the performance. That stopped being the case around 2000, 2004 was the inflection point, where processor, instead of being faster, they start including more cores. That's one thing. So now we have multiple cores, and if you want to use multiple cores for a single problem, we are talking about parallel computing. So that's what it is. And around 2006, people realized that these devices that people use, called GPUs or graphic cards, could eventually be used for doing computation, for doing math. Why? Because this kind of devices were created for calculating, for example, rotations when you are playing a game, and the objects in the game, you change the point of view. Well, there are a lot of rotations involved. There are calculations about how light impacts on the different textures, and how that change the image that you see. So what is happening behind those GPU cards is a lot of very simple math. And needs to be a lot of that simple math. So if your problem can be recaused in a lot of very simple math, it's probably that you can take advantage of those devices for computer. So I think around 2006, if I'm not wrong, NVIDIA, which at that time started becoming an important player in that realm, GPUs usually for gamers, usually for games, and more professional for people doing, for example, modeling simulations or architecture or engineering of that sort of applications. Well, these kind of devices can be used to crunch numbers, and that trend took impulse, and today they are very important. They are in a significant portion of the computational power of the largest supercomputers. We will see that in a minute. So with those machines, the GPUs, which are also devices that are capable of doing many independent, almost independent, simple math, we are talking also about parallelization, parallel computing. So we have the CPUs, we have the GPUs that are also doing some parallelization inside. And we have HPC clusters, which are a bunch of machines that can work together. So if they can work together, well, they need to communicate between them what they are doing or what another machine needs to do its job before it transfers a portion of the result to another machine, something like that. So all those basically three elements, the multiple cores, the GPUs, or accelerators, in a bigger scope, GPUs is just one example of what we call an accelerator. And multiple machines, all that is what we call heterogeneous parallel computing. We will be covering a little bit of that, but with a special focus and a special light on GPUs. That's what we have. So today I am showing you this image. Also, I showed yesterday. Most of the, let's say, this is an image of 4 supercomputers, not the 4 of the top 10 supercomputers. On the left side, you see 2 supercomputers, number 1, number 5, right now in the top 500. Top500.org is a site that has been for like almost 20 years, I think, more than 20 years, have been compiling, let's say, the list of the fastest supercomputers that people do a certain benchmark called impact, and for them people can make an ordering from the fastest supercomputer based on just one benchmark. That benchmark is basically a big linear algebra problem, so it has a huge bias toward that thing. So it's a big linear algebra problem, and these machines crunch that, solve that problem, and the machine that is capable of solving the fastest, well, we get the number 1 after the number 2 and all that. So this is the machine number 1 in the world today. It's called Frontier, and it's an Oak Ridge National Lab. Number 5, it was number 1 in 2018. Now it's number 5. Is Summit. And we have on the right side a couple of machines, the top 500 from the Chinese side. So Songwei Tianhu Light and Tianhe Chu. Well, I probably pronounced those incorrectly, but they are top 7 and top 10. The main message here are several things. One is that GPUs are present at least in more than 168 from a document that I found in the top 500. More than half of the supercomputers use some sort of accelerator, not necessarily NVIDIA, some sort of accelerator. So accelerators have been important devices present in those big supercomputers. Not only that, more than 50% of the computational power of these supercomputers comes from those devices. Doesn't come from CPUs, doesn't come from, even if they have very powerful and many CPUs, most of the power doesn't come from the CPU side, they come from the GPU, from accelerator. Just to give you an idea how big those machines are, I picked just the specifications of a couple of them from the American side. So Frontier, which is the fastest supercomputer on Earth today, they have this kind of accelerator. So it's an AMD Instinct. So they have a bunch of those. In terms of CPUs, they have more than 8 million CPU cores. This benchmark give you an idea. You run the benchmark, you set up a few parameters for the size of the problem, and from then you compute how many floating operations per second this computer is capable of doing. So if something is capable of doing just one operation per second, which is roughly, well, it's still faster than a human can do. Normally, that is called a flop. So a kiloflop will be 1,000, a megaflop will be 1 million, a gigaflop will be 1 billion, and here we are talking about petaflops. So actually, it's more than 1,000 petaflops, so it's an exaflop. That's how this machine. So those are millions of operations per floating point operations with real numbers. That's how we measure. That's a typical measurement of the performance of a GPU, of a cluster, of a supercomputer. So we have here two measurements. So one is the pencil and paper calculation based on the specification of the machine, how much it can go, so how far it can crunch numbers on paper, theoretically, and the reality. So no, sorry, the measurement is here, and the theoretical is here. So it's very significant how close they are from the theoretical for this particular problem. This is a very academic kind of problem. In reality, in the real life, the performance of a supercomputer doing real stuff is much lower than the peak performance, of course. And the power. So the power of this machine is roughly kind of half of the power used in a city like Morgantown. So it's like a small city. The amount of power that these machines consume, something like Morgantown. On the other side, this is Summit, which I told you was the fastest supercomputer a few years ago in 2018, and they have these GPUs, NVIDIA Volta V100. So this is the number of cores, CPU cores at that time. Compare this with the 8 million. So now we are most likely will be covering more than 10 million. There are machines with more cores than this. This is not, there are some other machines with more cores than this. It's just that this machine in particular perform better. And the peak and the theoretical. So notice the difference between the number 5 theoretically and the number 1 today. So there is a huge difference in performance, how these machines are getting extremely powerful computational. So now, with that, we come back to reality and to our reality and explain a little bit what we have, and which is on this two HPC cluster. So we have 2 clusters, for everybody. in West Virginia can request an account with us. In higher education institution in West Virginia, they can request an account on our systems, and we have two systems. You will be using Thornyflat. It's this machine. This machine has 178 compute nodes, so like computers, independent computers that can work together. So they are located here in those 3-4 racks that you see here in the image. So they are packed there. And we have a total of 6,500 CPU cores, the aggregated number from all the compute nodes, and a total of 47 GPU cards. And most of those GPU cards, as I mentioned here, they always have P6000, RTA6000, and A100. I will explain a little bit in a minute specification and use of one of those to get an idea how you read the specifications of a GPU card. On the other side, we just received very recently, a couple of weeks ago, and it's still in preparation, and our newest cluster, which is DollySots. It's right here. It has 37 compute nodes, an aggregated of 1,248 CPU cores, and 155 GPU cards. So this is a cluster that is much smaller if you compare with the number of compute nodes, but it has a bunch of GPU cards. Most machines have, well, let's say 3 or 4 GPU cards. On Thornyflat, most of the machines, they have 3 GPU cards per node. So the kind of GPU cards are newer, are A30, A40, and A100. So the latest model of A100. So this is the new cluster. And this new cluster will be specialized and will operate only for applications that require GPUs. Not for, there are many applications that could be intensive, computational intensive, but doesn't use GPUs. So, and you will see that using GPUs is not a trivial thing. So not just because you have an application, you just run on a GPU and magically it will perform much better. Not necessarily, and many applications today cannot take advantage of GPUs, so they should run on Thornyflat, which is a more generic HPC cluster. So a GPU card looks like this, something like this. This, for example, is one of the GPU cards that we have on Thornyflat. So most likely when we run something that you will see that the cluster that you received was an RTX 6000 or a P6000. The P6000 was the previous generation. This is the kind of GPU that you will most likely receive. Most of the GPUs that we have are of this kind, of this particular model. And we have like 3 of those on the machine, on a GPU compute node. Just to give you an idea, I collect the specifications of our 2 main GPU cards that we have on Thornyflat. The P6000, they have like a generation, and the name for the generation is called Pascal, and the Turing generation is the newest. So one important element to read this, one of the things I tell you a little bit, it's not 100% true, but it's one of the measurements that you can pay attention when you read this quickly, is the number of CUDA processors. And don't confuse this number that you see, CUDA processor, CUDA cores, with CPU cores. Those are completely different things. They are not comparable. So here the numbers of that usually is in the thousands, while the numbers of CPU cores on a typical machine is just a few tens. So 10, 20, 40, something like that. So again, CUDA cores is not something that you can compare with CPU core. In the case of this machine, we have 4,000 CUDA cores. This is one thing that you see. And the CPU, the clock rate plays a role still, but you will see that the difference is not that impressive. So another element are those tensor cores that some newer machines, new GPUs offer, and they are using a even narrower set of applications inside GPU. So deep learning can take advantage of that, and some other applications could or could not use the tensor cores and specialized kind of math crunching device in those GPU cores. So that's one thing. And another very, very important thing in a GPU card is the amount of memory that they have. Those devices have. On a GPU, on a machine with the GPUs, one thing is the memory that is attached or is associated to the CPU, and it's completely different from the memory that is inside the GPU. We will see, I think, more clearly when we present, I will present you a few examples with CUDA, when you explicitly have to move data from the main memory or the host memory, it's called host memory, to the GPU memory or device memory. You have to move data there to process, for the GPU to process that data. And at the end, the result, you need to copy back to the main memory. That procedure is expensive. That's the reason why it's not trivial to use a GPU for all applications. And that is one of the limitations that you have when you have a GPU card. Are all the numbers that I need for my simulation or my processing, my modeling, capable of fit on, for example, 24 gigabytes of GPU? If that's true, okay, I can put this problem on these GPUs. Otherwise, I have to figure it out the way of moving data in chunks. That's another possibility. Or using multiple GPU cards and divide the problem in such a way that I don't have to put all the data on a single GPU card. And I can distribute that a little bit. So that's another element. In this case, both GPU cards offer 24 gigabytes of RAM, which is kind of the minimum today for this kind of systems, around 24 gigabytes of GPU memory. That is, for example, if you compare this with the kind of GPU cards that you see for people who buy those for gaming, and they are usually 8 gigabytes or 4 gigabytes, 8 gigabytes. That's okay. That's normal for gaming purposes. But for crunching numbers, they are completely different. Another difference, by the way, if you try to compare, let's say, consumer level GPU cards with this kind of card were meant to run 24/7. So they were created to sustain the load for a long period of time without eventually breaking more or burning or something like that. In the GPU cards, they are more intended to create a burst of power that eventually will lower and the device will cool itself. So it's not meant to put them under a constant stress for a long period of time. So there are differences between the GPU cards that we buy and the GPU cards that someone can buy for gaming. The power consumption, you see these devices consume a lot of energy. When you compare with the computational power that they produce, they give you a very good balance. So, say, computational power per watt is very favorable with GPUs compared with CPUs, but still those machines consume a lot of energy. That energy, for the most part, almost 99% is converted into heat, and that heat needs to be dissipated. So that's why when you have this kind of machines, a big bunch of the problem of this is how to dissipate the amount of heat that these machines produce. And we have like 4. So in total, we have, imagine we have like 1000 watts, so which is like 100 bulbs, the old ones, in a very small space, all producing heat. So you need to dissipate all that really, really fast. Otherwise, it will melt the components. And a little bit more into the software side, another element that you read are the CUDA capabilities or the CUDA version supported in those devices. That is something that usually you don't, if you're running with deep learning applications, if you are at the application level, you probably don't concern too much about it. When you install, you prefer the system, it will use the common ground or the version that is adapted for the specific GPU card. But if you go deeper into the operation of the GPU card as a developer, as a programmer, you pay attention to these kind of numbers. So today we are around 8. So the newest versions are around CUDA 8, CUDA 8.5. So you capture that number, and that will give you the list of features, the internal features that the GPU is capable of understanding. So that is a little bit how this work. And now going to a more practical stuff, I will show you a little bit first in practice how you know that you have access to a GPU card. That's one thing. So we will see this in a minute. Is with this command. The host, the login node, the machine where you connect first, we see to the cluster. This machine has no GPU cards, so you execute this, it doesn't even exist. On a GPU node, a GPU compute node, you can execute this command and check, have a look on how many and which GPU cards you receive at that moment. And typically you get something like this. So in this case, I got a machine. This is just copy and paste of the message that I got. And that at that time I got that I was running on a machine with 3 GPU cards, 3 P6000. And you see here that they are not doing anything. So I just got those 3 GPU cards, and they have 24 gigabytes of GPU memory on them each. So 24 gigabytes here, 24 gigabytes here, 24 gigabytes here. And the power consumption of those GPU cards is 250 watts. So you get all that, you get the current power consumption, you can get a few specs from the machine by using this. On the contrary, we have one machine. We have just one machine with a bunch of GPU cards, and this is, for example, what you get. So we have this Quadro RTX 6000, and we have a bunch of them. So 8 from 0 to 7. So we have 8 GPU cards here, and we will see that in a minute. Another thing that is important here is how you request a compute node for interactive purposes from the command line. This is one thing. I will show you at least for the deep learning, I will have an example where I'm using one GPU for training a model and how that works. That is probably the main purpose of this workshop, is show you how you can request GPU compute nodes time with GPU cards. So this is the command. I will use it in a minute. I will copy and paste this. So if you use it, you will get, for example, one machine. Even if the machine has multiple GPU cores, you will get access to just one because you request just one. So it will adapt a few variables, so you only see and you can only operate one GPU. And in this case, we got one of the best, is the A100. This particular GPU card, let me see, they have 40 gigabytes of GPU memory. So here you have to decide how many GPU cards you need, for how long, the amount of time, the number of cores. Typically, you should request 8 cores per GPU. If you want to use one GPU, request 8 cores. If you need use 2 GPUs, you request 16. If you want an entire machine, you request 24. So the GPU compute nodes that we have on Thorny, they have 24 cores. So now let's go in practice with this before we move on into the other sections. I will show you here very good. This is still working. Okay, but I can probably close it here just to show you. I just entered here. You see on the instruction here. If you go here, from here. So if you go here to the web page, the instructions are right here. How you access Open on Demand. So you click here on demand on this link on demand-tf, and you enter your credentials, your Duo, and you land in something like this. This is the dashboard for on demand. From here, for example, if you need a terminal, you click here in clusters and Thorny Flat, and you create a terminal. Otherwise, another thing that you can do, if you are using an SSH client, you can jump directly, or directly no, you can use the SSH client to connect into the WVU gateway, and from that machine, you connect to Thorny, and you will get a terminal like this. So this is the command that you use for requesting one GPU for 2 hours with 8 cores for an interactive execution. So, and when I execute this, and if I'm lucky, in this case, we separate a little bit machines, GPU machines for this exercise, you will get pretty quickly something like this. Notice that we have changed on which machine we are operating. Here we are operating on one of the main machines in Thorny Flat. Here we jump into a machine with GPUs. This is a different machine. Notice that the name of the machine, which is here on the prompt, is different. The first command that I will execute is NVIDIA SMI. I show you. This is a command that allows me to see which GPU cards I have available for me. In this case, I got the older generation. If you execute it that way, you receive whatever is available. And they are not that different. So the P6000 and the RTX 6000, they are marginally, the RTX 6000 is marginally better. I think less than 10%. And they are comparable. On the contrary, the A100 is really, really special. So they have far more memory. So they are more intended for applications where really demand the extra memory, and they are more powerful too. So this is one way. This is one way of seeing that you can use a GPU. How you use the GPU is the topic of the rest of our workshop, is what you can do with this. So right now I have a GPU, I can use it. Well, I can do with it. We will see applications where this can be used. So this is the main purpose of this first episode here. And let's move a little bit into the next session, which is the different paradigms in parallel computing. And I will go relatively quickly in those that doesn't relate with GPUs, and I will spend a little bit more time with those that really have to do something with GPUs. So let's take a very simple problem here for the sake of the exercise. So imagine that we have a long vector, here, and we would like to do an operation with that vector, something like this, one example, or something like this, something that we are doing with a vector. So you see, one thing that I can do is apply the well-known, also in work conditions and also for many things, which is called divide and conquer. So you have a long vector, and you can see, okay, if I can divide this vector somehow, and what I have to do with each chunk of that vector is pretty much independent from what I have to do with the other chunks that I can produce. Well, I can use multiple workers, different compute entities that can take this chunk, operate with that, and somehow recreate the result just by joining the partial results from those workers. All that is, for the most part, the strategy that we use in parallel computing is divide and conquer. In this case, for this exercise, I am using one compiler, which is the NVIDIA compiler. The reason why I'm using this compiler is because this compiler in particular, the NVIDIA compiler, will offer me all the 4 different parallelization paradigms that I would like to present today in one single compiler. So it's not the only one, but it's the only one that gives me the whole range, easy access, and easy to see what I can do with them. If you load that, so we can do it right now, for example, here. So we can load this module, and we can see the version of the compiler that we are using. We are using the NVIDIA compiler that used to be the Portland Group compilers, the PG compilers. NVIDIA bought that company several years ago, and now they integrate and rebrand and rename the compilers. So now they are called the NVIDIA HPC suite, I think that they call that that way. So here you see the compiler that I'm using. And let's see how we can solve this problem, a problem like this, with different strategies of parallelization. So first, how you solve this from a serious perspective. The code is here in C. I will not enter in details. I will just mention that, okay, here we are creating a few vectors, and here we are doing the operation with them. So we are here computing the cosinus of the vector, and we are filling the vector A1 with that, and we are computing the sine, the sinus on a square, and getting B, and after we are taking that vector, getting the difference, and producing the result. That's the serial version of this code. Let's say the important lines of code are those that I'm highlighting here. Everything else is just to create the vector, to populate the vector with something. And so here I'm populating all that, and here I'm just showing the result, and that's it. So I'm printing the results, and that's the purpose of that. So I will not have time to compile that, but if you take this and you compile it, you see that the code works, and that's what it has to do. This is the serial version. In this case, If you compile this and you execute this, you are using just one CPU core. There is no way that with this code uses GPUs. No, it will not use GPUs. It will not use, if you have multiple cores, you can have 40 cores on that machine, and it will not use more than one. This is the serial version. So now we see, okay, that's the best that we can do with just one core. If you need faster, well, you have to buy a faster CPU. That's the best that you can do. Now, the next thing that we can do is to try to think, okay, can I apply the divide and conquer strategy to solve this problem? And you see, well, for the most part, yes, we can use the divide and conquer. We can take this vector. If you see here, there is no reason why we cannot split this problem here in chunks in such a way that the multiplication here, the cosinus, the sinus, all this operation can operate on smaller chunks of this and distribute that to multiple cores, at least that we can do. And that is exactly what we are doing here on the next section. So we will explore the next way of parallelization a code, which is using the multiple cores on the same machine. Our compute nodes, for most part, they have 40 cores. In this case, we have on this machine where I am right now, they have 2 sockets with 12 cores, so we have 24 cores, CPU cores, and from those I just request 8. If I try to use more than 8, all the processing will be squished in 8 cores. So 8 cores will be competing to get this done. So now the next strategy for parallelization is OpenMP, is shared memory parallel program. In this case, we take advantage that all those CPU cores see the same memory. All the memory on this machine, by the way, is 90. So this is a small memory machine. So we have 96 gigabytes of RAM. This is our definition on Thorny of a small memory machine, 96 gigabytes. So what we can do? Okay, there is one technique called OpenMP, and most compilers support OpenMP. The 3 main compilers that we have on Thorny Flat, which is the GCC compilers, the Intel compilers, and the NVIDIA compilers, all of them support OpenMP to a very recent specification, 4.5 or something. So all of them support this. This is a very simple way of parallelizing a code. Very simple. All that you have to do is on a very specific places, put a few comments like this. So this is called this comment here. From the point of view of the language, from the point of view of C, this is a comment. Well, this is a directive. The compiler will ignore that. It doesn't know what to do with that. Or pragma. And so those elements in very specific places will instruct the compiler to parallelize the code in such a way that it can divide that into multiple cores, and those cores will operate on portions of the vector, for example, in this case, the vectors here, and all of them will be writing the result on memory. And by the way, the memory is the same, so all of them are basically seeing the same pool of memory, the same. It's just that they are writing in different location of that memory. So that is the advantage, and that is the beauty of a scheme like this, OpenMP. So just is the same code. If you compare, it's exactly the same code here. So you basically take the serial code, you take the code that works serially, and you add a few pragmas, a few lines like this that will instruct the compiler. The compiler will say, okay, parallelize this section. This section is parallelizable. You can divide that in chunks, do it. You have this. And for something like this, if you are using 40 cores and the vector is sufficiently large, it pretty much gives you linear scaling. So you have 20 cores, and at least for a problem like this, again, if it's sufficiently large and you execute it, you pretty much get the result in 1/20 or 1/40, depending on the number of cores, the amount of time that used to take compared with the serial code. So in a fraction that is basically divided by the number of cores that you have. This is one way. At this moment, we are not using GPUs. We are using multiple CPU cores, but not GPUs. Now, the next strategy that is still not using GPUs yet is distributed parallel computing. In this case, we have to change entirely the code. You have to take the serial code, put it aside, and you have to basically rewrite the whole thing. The reason for that is that the way it operates is completely different. Now we have multiple machines, multiple compute nodes that will work together to solve this problem. They do that by communicating between the different compute nodes. That communication is called a message, or that communication message passing. And MPI stands for message passing interface, an interface for passing messages between machines. Now, we have on Thorny Flat, and we have also something similar on DALI-SALS. We have compute nodes that are attached, or they are connected with a very, very fast network, such that this communication between compute nodes happens very, very quickly and can move a lot of data between from one machine to the next one. Let's go quickly on this. You have to rewrite the code. I will not enter in details on that. You can copy and compile this. I think that I have the instructions. I probably not even put instructions for compilation, but that's not the point. The point is, this is another way of parallelizing codes, using multiple machines, put multiple machines to work on the same problem. Again, using divide and conquer. That's it. Here I'm explaining a little bit how that works. And now we move into real heterogeneity. So if you want, the first heterogeneity that you can imagine is a code that uses multiple machines and the multiple cores on those multiple machines. That is the first heterogeneous parallel computing that you can imagine. So joining, for example, OpenMP that we saw here, OpenMP plus MPI, or OpenMP, yes, OpenMP for multi-core parallelization and MPI for distributing parallel computing. That's the first kind of heterogeneous parallel computing. But now we would like to bring GPUs into the table in the play. One of the strategies, before I move into the other side, like which is one first way, is something called OpenCL. This is like an extension of the language that allow you to compile codes for different brands of GPUs or accelerators that support OpenCL. It's not trivial. The code is, as you see, looks complex. I will not enter again in details, just to give you the flavor of what it is, how all of boilerplate, all the code that you had to write just for doing something as simple as taking two vectors and multiply those. So there is a lot of boilerplate here, a lot of things that you have to do, preparing memory here, preparing memory in the host, preparing memory in the device, copy the memory and all that. A lot of calling routines just for doing that. I think the central part of this code is, let's see, I think is right here. Right here. But for that, you need to fill a lot of code for getting that. Now, this is one way. Now let's move into something softer, but still using GPUs, which is called OpenACC. OpenACC looks very similar to OpenMP, with the advantage that now you can use GPUs. And you can decide if you want the code to run with GPUs or you want to distribute with multiple cores, like a la OpenMP. And it works very similar. You just put some pragmas here on specific places for OpenACC, where you say, okay, please parallelize this section. This section I would like to see it parallelized. And during compilation, you decide if you want to compile that for multi-cores or you want to compile that for GPUs, which kind of GPU you want to that to be compiled. And that is a very simple approach for parallel computing with GPUs. I think the easiest way of using programming GPUs is OpenACC. And again, you basically take the code, the serial code, the code that works for you before, and you just put some pragmas here and there, and you run some profiling, decide which part are the critical ones that are consuming your time, and you parallelize those, and you get advantage on those sides. So very simple, relatively cheap to get good results, sometimes very impressive results with minimal changes. It's OpenACC. And now we are using GPUs with this. Now, the next level of that, in particular for GPU cards, is using CUDA. With CUDA, you use like an extension of the language. It's something that is beyond C, or for example, you put lines of code that from the point of view of the compiler or the compiler, they are completely wrong. There is no C code. So you need to compile this with another compiler first that will in the background do a lot of things to write the proper C code that will be compiled with C later on. So that is called the NVIDIA CUDA compiler. So if you go back, we go back here, and here I execute the version. This is the C compiler, the NVIDIA C compiler, which is different from the NVIDIA CUDA compiler, which is this one here. Well, voila. This is the CUDA compiler. Yeah. Notice the differences. For those of you who understand a little bit of C, you have something that really doesn't look C, is right, something like this. You see this kind of things here. This is not C code at all. So you are basically, and in this case, another thing that we will see more clearly in the next session, you need to copy data very explicitly. You need to do everything. You have to do the heavy lifting directly on your code. You copy from the main memory that is called host memory into the device. It means the GPU card. So you are copying the vector A and the vector B from the host to the device, from the main memory to the GPU card. Do the operation with the memory that is on the device that I put here with D underscore. So this memory is on the GPU card. So they will do all the operations and the results will be on the GPU card. And now after I have to copy the memory from the GPU card, that is the memory that is here in D_C on the device and the GPU, and copy back to the host memory, to the CPU card, to the CPU, to the main memory, the memory that the processor can see. So all that work happens with CUDA. Hopefully you don't need to use CUDA, or if you are at the application level, you don't worry, you will be doing deep learning or molecular dynamics, all that. If you really need to program, you will first try to do something quick with OpenACC, for example. And if you're really wanting to the details, so that justifies for some purpose in the research, or you are developing a code where this is important, yes, you go into something like CUDA and start writing this kind of code. And so you see here, this is just an example of what is happening, and there is some explanation here on how this works, and the copying of memory here and there. So now let's move on to the next session here. Again, the purpose here is not learning programming, just to give you a flavor of what it is, how that works. So when you start operating, for example, the application level, you get an understanding why a GPU is important, for example, for neural networks, why this is good for molecular dynamics, why this makes sense for certain application, and getting an understanding if maybe this works for me or is too much, if I can go into a GPU and take advantage of that, or that is out of scope and it will be not worth the effort. So let's go very, very fast on CUDA to get an idea, mostly the images, not the code, to get an idea how that works. So the idea here is that inside the GPUs, they have a bunch of circuitry that is capable of doing math operations as a group, as a cluster of devices, small devices. Those are the CUDA cores. From the logical point of view, what you process are threads. And those threads are agglomerated in what is called a thread block. All those thread blocks are executing exactly the same operation, eventually on different data, and all those thread blocks are agglutinated, or they are organized in what is called a grid. So that is the ordering of that. So you have one device, you can have multiple devices, but in one device, you have a grid, at least one grid, and the grid has blocks, and the grid could be one-dimensional, two-dimensional, up to 3 dimensions. This is just a software organization. It's a logical organization of a grid. So how the blocks are organized, how you address the location of those blocks, and you operate with them. So this is how this works. The main message here, because I really want to not spend too much time on this, you can read it if you are interested. Most of you are not interested on this low level of understanding. Or low level means closer to the device, closer to the machine, closer to the programmer. It's just to give you an idea how you organize those. So here I think is where you organize the block. See here in this kind of sections here, you are deciding, okay, what is the size of the grid? How many elements do you want on your grid on each direction? If you put just one, is just one direction, so one unidimensional grid, and the size of each block. And typically the size of those blocks, for performance reasons, are multiples of 32. So that goes deeply into how those devices work internally. But usually it's something like this: 256 is the block size, and this is the grid that you create. And I will not spend much time on this. I really want to move quickly into deep learning, the first application that we will see today. So that's it. So main message here: GPUs work moving memory into the for operating with GPUs, you have to move the memory from the CPU to the GPU, and when the result is complete, you move the data back. This is the first thing that you have to keep in mind. Second main message: when you are operating with those, internally, from the logical point of view, they organize all those CUDA cores working on threads, working as groups, doing the same operation. Those threads are organized into grids and blocks, and the grids and blocks could be one-dimensional, two-dimensional, three-dimensional, and with those you organize your processing that makes sense for you. And the size of those blocks, the size of those grids have an important consequence in terms of performance. So a lot of the time spent on tuning this kind of CUDA applications has to do on which is the best way of selecting the block size and the grid sizes and the organization of that, such that they perform the best, which is non-trivial. There are some guidelines, but that will be beyond this. So let's move on to the next session. You can read this on your own if you are interested into getting a little bit deeper into that. So deep learning. Deep learning is the first application where GPUs or accelerators in general shine. So let's understand a little bit what deep learning is, and at least my main objective here is two things. One, understand why GPUs are very good for deep learning. This is one thing. And second, in practice, how I use those things on Turing Flat, on Dolly Salt, how I can run models. That how you learn to build models will be beyond what we can do in 1 hour and 50 minutes. So deep learning. Deep learning is a subsection of what is called machine learning. And machine learning is a subsection, or a subset, what we call as artificial intelligence. There is a lot of names here that could be misleading, very misleading, or yes, that could be like buzzwords if you don't understand those correctly. Starting for intelligence, so has nothing to do with intelligence, with the intelligence of human that we associate for humans. And the best way, well, and that's one thing. I will go into the metaphors. Machine learning has nothing to do with the way humans learn. So that is another thing that could be misleading, thinking that the machine is learning something. They are not in the human sense, probably in the machine sense, but that's another thing. So that, and deep learning, what is the meaning of deep learning? What is the deep of learning? What is the meaning of what we call it deep learning? So a lot of this, the idea to keep in mind, the metaphor that I always apply is machine learning will not tell you anything about how humans learn, as artificial intelligence for most part will not tell you anything about human intelligence, as learning from an airplane will not tell you anything about how birds fly, or how learning from submarines will not tell you anything about how fishes or whales swim or operate in the water. So there are different things. We say they are, the plane flies, but we are not meaning that they fly as a bird or was an eagle. No, they don't have anything to do with that. So it's a little bit like that. So the name is just convenient, but we understand it is misleading. So deep learning. Well, machine learning, for the most part, the central topic of machine learning is learning from data or creating models that improve based on data provided to them. So instead of giving the equation that solves the problem, which is the typical way you present things to a computer, if you are computing a ballistic trajectory, you know the equation that the projectile will follow under some idealistic conditions. So you can imagine that air is not present, so just gravity, and the world is flat. So if you take those things, so yeah, you can compute ballistic trajectories just like a parabola. If you start adding elements to the model, you get a more refined version of the solution. So you add air, so you have now another force that is with the square of the velocity. With you start adding things that to the model. But in at some point you get an equation and you put that equation into the computer, and the computer later, with that given initial conditions, can produce the propagation of the projectile. In this case, instead of giving the equation, we will give them examples of the trajectories that certain projectiles under different conditions are following. And we expect that the computer somehow came with a model, came with a way for predicting what will be the trajectory of another object that is not the same that those that we presented before. And so it uses the examples, it uses the data to create a model that is capable, for example, of predicting trajectories or predicting the outcome of something based on those examples. And that is machine learning. Now, a section of that machine learning is called deep learning. For making those predictions, what we usually do is transforming the data. And I have here, for example, one example of what this means. Imagine back in the Middle Ages, people was seeing on the sky the location of the planets. The planets were like stars, with the only difference that they move. So they are something special with those stars, because compared with the other stars in the sky, they are moving. They are changing location every night, so they are moving. And we say that planet Mercury or Venus or Mars, they move around the Earth, which is correct. Those planets move around the Earth. From the perspective of someone on the Earth, they are moving around us in a very convoluted way, sometimes returning, some ways going backwards and moving forward, doing very weird kind of movement. But that is correct, is the planets are moving around the Earth. Now, but if we do a transformation and we manipulate the data in such a way that we consider that we are actually moving around the sun, and those planets are also moving around the sun, you transforming our observation, changing the point of view with that transformation, considering the sun as the center, we get a simple picture. And that's why we say, okay, our planet, the other planets are moving around the sun. And that's what we see. And the curve that those planets describe fits better under that description, that is considering that the sun and those planets move around the Earth in a very convoluted way. So that is transforming data. So that is one way we see. And here are some pictures on real tables of people compiling the movements of the planets. And from those tables, later scientists start to develop models to describe those moments under different circumstances, under different assumptions. Okay, it's the sun, and we move, and the movement is not a circle, it's an ellipse. It's an ellipse. So all that are transformations to data. So now what we are doing is very similar to that. We are taking some data and we are applying some transformations to that data. The reason what we call deep learning, which is almost a synonym of neural networks, is that those transformations happens in multiple layers. So we are transforming something, and after transforming what we just transformed and taking that and transforming back and transforming again and again and again on multiple layers. So we are getting deeper in the number of transformations, and those transformations is what we call learning, the deep learning, basically. That's the reason, that's the origin of the name deep learning, is transforming. And we say learning because if we do this, for example, from the scientific point of view, from the scientists who collect those data, so they took all that data, took all those convoluted ways that as Mars goes back, they go back and they later go forward on the sky or Venus or all them, and put them under a different point of view, a different perspective. And they realize that the sun is in the center, and that fits the description much better. And the planets are moving not around circles, no matter how perfect those circles could be to our Platonic desire of those being more perfect. But the reality is that they move, for most part, something closer to an ellipse. So all that. So knowing that the center is, this is knowledge, and this is all what we learn from those observations. In this case, we are just creating models that produce a result. And unfortunately, we are losing a little bit the knowledge. We don't know what those things work, the way they work, they just work. So they are more utils of engineering. They are not telling much about learning itself. And that is the same with deep learning. That is the same with those large language models that will not tell you anything about language at all. They just work. They just are feeding an equation. And that's the next section that we will see here. There are two ways of presenting deep learning, or the origins. Again, now this is misleading way. One is from the biological neural networks, where we are taking inspiration from the brain, or from neurons, to build something mathematically that works like those. But we are not claiming that our brain works like an artificial neural network, or that a big neural network will start behaving like a human or like a brain of some sort. No, they are not. This is a long shot. Let's say this is pure math. And if you consider it as a pure math inspired with something, that's okay. If you start making extrapolations, you will start getting into the realms of line or stretching reality, which is stretching reality is more the realm of politicians, is not the realm of science. So that's one way. Another is per perceptron, which is again a mathematical entity, a mathematical construction that was created back, I think, in the 80s, I think, 70s, 80s, I think, or even before, for example, for classification purposes. So we are trying to get a function that is capable of separating or categorizing a few entities based on the values, the configuration associated to those elements. Those two ideas we consider are the origins, at least from the point of view inspirational, of what we call today neural networks, and those we consider equivalent to deep learning for most part. And this is what a neural network looks like from the mathematical point of view. So we have an input layer. So we have all the data coming here, and we have some layers of transformation. And eventually we have multiple layers of transformation until we get some output. And the output could be compared with some known output, and we back propagate, we adjust the parameters here inside those neural networks in such a way that the next time that we put some input, we get closer to what we get. That procedure of adjusting the parameters inside is called training. And when we get those sufficiently refined, we say we have a trained model, and we can use that trained model to put something new and get the result for that, even if that input has never been presented to that model before. That is the whole game of neural network. So so here, for example, I have like a visual perspective of what a neural network is doing, or what you expect to do. For example, for classification, you have two curves, and you want to separate the word somehow, such that all the points that we associate here on blue, we consider belong to the blue category, and all the points here that we put in on red with a simple line, we will consider belong to the red category. And you see here, without any transformation, there are points here. Blue portion of the red line is in the blue zone, and also portion of the blue line is in the portion of the blue line is in the red zone, portion of the red line is in the blue zone. But if we start doing transformations to the space, in this case, to all this space, we can get eventually ways of cutting the space in such a way where it's very clear which side of the world belongs to the blue side and which side of the world belongs to the red side. A neural network is basically doing that. It's changing the space, changing the elements here, a little bit like we think about with the planets, changing the point of view, changing the space, stretching, and doing some changes in such a way that later results very easy to distinguish which belong to which. This is another way, very visual way of seeing how a neural network is changing the space with basically two elements. What the beauty of neural networks, at least at this level, is that it's very simple. What the math they are doing is very basic linear algebra. So they are doing rotations, they are doing scalings, and just the sweet sauce here is one linear function that you put on top of all that, that will do the squishing, that will do the stretching, the nonlinear part of that. And that is what allows these neurons to distort the space. For example, for this problem here that starts with a spiral, is twisting the space in such a way that when at the end it stretches, and you get a clear separation between the red zone and the blue zone. And here is another neural network that is trying very hard, is stretching all the way that it can, it tries, but never reaches a solution, never succeeds at stretching the space. You can never cut it. So this is the kind of things that a neural network is doing. Simple math with a tiny dose of nonlinearity, and that's it. That's the magic. This is a neural network again. Let's say those neural networks could become very complex. They could have some extra elements to that. So this is like a small zoo of different variants of neural networks. We will not go into deep into those, but they have its own use, they have the purpose, they have been created because they serve a certain purpose. That non-linearity of the function is, in mathematical terms, is called here the activation function. It's again inspired on the biological neural networks up to a certain extent. And these are a variety of neural of activation functions that people use. And the most classical, well, use something like the logistic, something other logistic step, but in real life, people use these ReLUs, these rectified linear units, for example. They are very practical, easy to compute, and they produce sometimes better results. So at this moment is pure engineering. Is what it works the best with the less effort in the best way. So those are just to give you an idea of this special ingredient is something like this. So nonlinear functions like those. And from the math point of view, and this is the main purpose here that I want to stress. And here I am making a small example of a neural network, very simple neural network. I'm putting some numbers here, and I am propagating this network. So if you see here, what all that we are doing at the end here, all these operations can be summarized in just linear algebra vector matrix multiplication. It's just that. And that's the reason why GPUs are so good at this. Because if you remember, I told you GPUs originally were created for doing rotations, for doing scalings, for computing what happens with the ray of light impact with a certain surface. So they are doing that kind of math. Rotations is a matrix. It's a matrix that on a vector it will rotate the matrix, it will rotate the object. So all that simple math, very simple math, but executed on a larger scale for many elements is the reason why those GPUs were created in the first place. And that's the reason why this simple math works so well on GPUs. So if you can put, imagine this is for a very small neural network, by the way. This is something like this. A neural network is still small, looks like this, but typically these neural networks here, they have thousands of elements here, and they have tens, even hundreds of layers deep. So you put all that, and those are big matrices that need to operate in cascade to get the result. And after, you need to change the parameters of all those, the parameters in this case, for example, basically two things. The parameters is here, this WI here, and this bias, this B here, all those elements. You change those elements and the neural network will produce a result different. If you adjust those smart enough, you will get the result that you want for the element that you present. So the next time that you present something similar to that will produce a similar result at the other end of the neural network. So you see, very simple math, no more than linear algebra, and that's the reason why GPUs are so good at this. I will not go into back propagation. This is the central reason for a neural network has to do from the math point of view, but I will skip it for the purpose of this workshop. And a special kind of neural network is called a convolutional neural network. They're particularly good for visual problems, for computer vision. And in this case, what we are doing is something slightly different compared with those densely connect neural networks. This is called a dense network. Here, what we have are matrices. Here is like a picture matrix, and we have some smaller picture here called filters. We operate with those filters, like imagine that you overimpose the filter on top of the picture and you compute the sum, you compute a very simple operation. Still, it's a matrix sum, matrix operation, very simple. Again, GPUs are perfect for this. And the next, and you compute this and you get the result. And you put the result here. You get something that it summarizes somehow what happens to this portion of the picture under this filter. Some of those filters will naturally produce values higher when there are edges, or when they have curves, or when they have something. And that's the reason why we apply this, and the next time we move with a shift, we move this filter a little bit, we do the math again, and we got another number, and we put the number here, and we do all that with those shifts. So it's repetitive, boring math executed over and over and over, thousands, millions of times. So simple math in a big scale is all that those GPUs are doing, and that's why they're so good at those. So you see that this is pretty much what they are doing. There are other kinds of neural networks. I will not go into all the details of that, just for you if you want to read about this. I will probably not describe this. Again, the document is there. You can read it. It's a little bit review of the history of the main milestones of neural networks, where at which point convolutional neural networks became important for visual problems. Now we have this breakthrough with deep large language models, which is not here in this, I didn't put in here. This is another kind of neural networks that we use. Today, if you see, there are basically 3 surviving. They used to have more, those Theano, Chenier, Keras, all those. At some point, those different engines were merging into big software packages. And today, usually I teach the 3 main frameworks, which are TensorFlow, PyTorch, and MXNet. And probably at some point I will include the big one from China, Paddle. So those are big engines, and most what you find the models, and they were built with those somehow, and then later are integrated in solutions, in codes. Once you train that a neural network for producing something, after you can create a small application on a cell phone, and the cell phone will run the neural network that is very light, that consumes nothing, and you can take changes on a picture, doing something, recognizing voice, or do whatever. At the end, after a model is trained, executing a neural network is very simple. The hard part is the training of that. It's millions of operations, a lot of time spent, a lot of tweaking happening to get this right, which is for most part trial and error with a lot of expertise. So there is a lot of heuristics behind this. This is where this becomes more like cooking and less like chemistry. So that is a little bit what I would like to present here. I would like just to show you a little bit how you operate with this, with a couple of examples. So let's do it first here. I have one to show you, and I will later tell you exactly where you can take this. So you click here, Jupyter Notebook. I will execute one Jupyter Notebook. This is the interactive way of running neural networks or training neural networks with from a Jupyter notebook. So here I select Python via Singularity. That's one thing. I would like to use GPUs. So I will be using the GPU Inter for interactive execution. I will request 1 hour. I will request 8 cores here, and I will request 1 GPU card. So we have like 40 GPU card, and we have 21 participants right now. So probably if you try to do this, you will get very quickly a GPU card. And I will ask Jupyter Lab. And here I have a variety of Singularity images that give you all those frameworks. So I will mention here, for example, what we have. Very recent versions of MXNet here, 23. These are, of, let's say, kind of official images that have been created for those frameworks, directly optimized by NVIDIA people. So we just took the image, we add a few extra things for us, and that's it. So we have MXNet here, we have PyTorch, we have TensorFlow version 1 and TensorFlow version 2. I think at least NVIDIA is not releasing anymore the TensorFlow 1. That's what I see. I think that they will not releasing anymore. This is the latest, the last version that I saw with TensorFlow 1. And the newest version is only with the TensorFlow 2. And so I will be using this for the example that I will show you in a minute. And TensorFlow 2306, TensorFlow 2, and that's it. So let's see. Python via Singularity, GPU Inter, 1 hour, 8 cores, 1 GPU, Jupyter Lab, TensorFlow 2. To click launch. And by the way, if you want to take in the meantime, if you want to see, make a copy, it's in share tutorials. Here I have a bunch of Jupyter notebooks, and I will be just running one of those. I will be running. Let me see which one I will run. Okay, well, I will run the 4A, the TensorFlow. They will say in parentheses which framework they need to use. So I launch that one with TensorFlow, and so I will be using that one here for demonstration. That's the first thing that I would do. So if you want, you can copy this location, copy the deep learning folder. I think it's not that big, it's 4.3 gigabytes. You can copy that. I recommend you to copy that to your Scratch folder instead of your home folder. But if you have a space and you want to try it, well, do as you prefer. And I think we have it now. I have my own copy on my Scratch, so I will be using that. And I think it's already there, so I'll be closing this, and I will be launching this one. So this is one way of running training with a Jupyter notebook. Convenience, you can add things. So let's see. So here, okay. I don't see the message. It's because probably you are requesting in a standby. It's probably your machine group. You are requesting that on a standby. On a standby, we don't have GPUs. So that is why it's failing for you. It should be here. It should be when you do it for, I will launch another one. Oh yeah, it's GPU Inter. Yeah. Okay. Okay, so here, so here I have this. I can see how complex that is. Okay, this one is relatively simple. Let's see. This is a very academic. I will run it entirely. I will, so you can click here, click all outputs. Let's see if I can execute. I don't remember how fast it used to run. So basically here, I'm using a classical example here, which is fashionist. It's basically tiny little figures of things like boots, coats, shirts, shoes, things like that. And the idea is to train a neural network that is capable of answering correctly when you are presenting with one element that had not been used before, an element that is completely new to the neural network. Distinguish if that is a coat or a shirt or a shoes or socks or something. That's what they are doing. So it looks like this. This is like a hoodie or something. And it should be able to answer, okay, what this image represents. So this is just an example of the images. They are very small, 28 times 28 pixels. So those are tiny images, very, very tiny. That they usually, you learn deep learning with this kind of examples, this kind of problems. And you separate, you have a collection of those, you separate a portion of those, and you put them in a drawer, you separate them, you will never use those because they will serve you to see if you are getting a good model. And from them, you take whatever is left and you train the model with that. At the end, if the model is good, you will try to see how good it is when you present the new data, those images that you just separate. And you also usually separate out in 3 sections, one for training, another for refining the parameters, and the final one for actually see how good the model is. So I will not go into the details on particular for TensorFlow, how that works, how you build a model. The model, for those of you who wants, is like this, is something like this. That this is how you build the model. You build layers, you stack layers here for this kind of very simple models that are called densely connected neural networks. And the important thing is happening, I think it's happening here in the training part. Here is where the GPUs are doing all the things. So they will tell you, I think, that they will tell you how many seconds they took to run for, let's say, they take the 28 pixels and they are basically stretching those into a long vector, 28 times 28. So whatever that is, the value. They will tell me what is the size. And the number of layers that you put. They will compute all those matrix multiplications that I just told you. The 784. So then you take that, you stretch those, and they do that. They do that for all the elements that you have in your training set. They took 4 seconds, 3 seconds, 3 seconds. You will see if you run this with CPUs, just with CPUs, without using GPUs, it will be around 1 order of magnitude or more slower than using GPUs. That's why they are so good. They significantly speed up the processing of this kind of neural network training. And at the end, you will see which are how the accuracy of the model, and you get some figures, and at the end you get something that you can use with this set that you separate before. So let's say you can follow this. I would like to just show you from the other side. I will be killing this. I think that at the end I have several procedures that I'm doing, optimizing those models, different things that I do. I will not go into that. This is not a workshop on deep learning itself. So I will be closing this. I will be closing this. And I will see what we have here. So I will be deleting this, killing this. I will show another, and in the last minutes that I have, I will show you on the other side how you execute, you submit a job for training a model from the command line without the graphic user, without a Jupyter map. So I will create another for this. So it will be exactly the same, Singularity, GPU Inter, 1 hour, 8 cores, 1 GPU card. And in this time, I will be using PyTorch. So you need to change, because each image was created for one particular framework, for one particular deep learning engine or framework. And so in this case, let me see which one is a good example here. PyTorch. No, this one. By the way, those are interesting, by the way. I'm not discarding it, just that they are pre-trained networks, so they are showing you what you can do if you know all the weights and all that, and you just want to play with something that has been trained before. Those are networks that have been trained to recognize animals or recognize photos. And so I took one photo, downloaded from Wikipedia, and I present that to the neural network. The neural network is recognizing the element. And the other is trying to convert, I think, horses into zebras. So they're doing cool things. And I will just probably go into this one here. See. Well, let's see this one. This is still interesting. So this one, I am using PyTorch, so that's why I load PyTorch for this one. In this case, I will be using a network that has been pre-trained. That they have a bunch of networks that have been used, that have been reported in the literature that be used before. So I will be using one, for example, this AlexNet. I already have all the weights, so all the numbers associated to each neural network. By the way, this is not the traditional network. This is a convolutional neural network. And here, what we have are all the elements of typical from a convolutional neural network. So all those small filters and things that reduce dimension, reduce the size, which are called max poolings, that basically are zooming into the figure to get less numbers, and all those in a very pile and stack of those, they end up being populating a dense network that will basically do the classification at the end. This is AlexNet. This is what is called AlexNet. This is the network that I'm using. If you run it, you will see the weights are from here. So in the data folder, I already have all the weights associated to this network. And the network basically will take a figure here of a box turtle, and I will take that figure, scaling the figure, doing a few pre-processing of the figure here. and I will present this figure to the network, and the network at the end, well, this is the network, by the way. I just print the network. The network has all these layers of convolutions plus max pooling, convolution, max pooling. This is the typical sequence of those things. And at the end, I have a big dense network, and that is classifying into 1,000 categories. So when you run for the pixels of that network, all those elements, you get something like this, a bunch of numbers. And you just pick which are the highest values. So they will tell you which is the probability of the picture that I put there is the picture of a hat or the picture of a car. So they will associate to those things very low probability, but they start associating higher probabilities to things that resemble more a box turtle. So which are the elements that I got when I ran this? I got this kind of values with these probabilities. So when you convert that into probabilities, it's a box turtle with 87.6 probability. Otherwise, a terrapin, which is kind of a turtle, is in the same group. Otherwise, it's a moth turtle. Okay, maybe with a low probability of something happening here. Oh, something I don't know what. But I never run it actually. I'm just showing the elements that I got when I ran it before. So we'll get you the, for example, here the 10 categories with highest probability, and you see there is a huge difference for this one compared with the others. So that is what I am doing. And in the last minutes, what I would like to show before I get this, we'll kill this, is here. Again, this is in share tutorials, deep learning in here in scripts. So in scripts, you will see this data folder that contains the images of handwritten numbers. This is another academic problem that we have. I have here the Python code for PyTorch for the model. I probably can see this better here. So this is the model. So here I am building the network. This is how you build a convolutional network here, and with some dropout, right? But some other things here. And here, what I'm doing is doing the transformations to the input, and you fit the model here. You build the model, you fit the model, and at the end, when everything is done, you get all those weights. Those are numbers, and you can store the model. That's what I'm doing at the end. I am storing the model on a zip file. So PyTorch allows you to store all the model and the values into a file, such that you can recover the model later on and use it or improve it or do whatever you want with it. And that's what I'm doing. So I'm saving the model, and just to show you that I can recreate the model, I am just putting those lines where I'm actually reading what I just wrote and recreating the model that I can use later for execution. So this is the Python code, and this is one of the ingredients that I need. The other is the submission script. The submission script looks like this. So here I am requesting one node, 8 CPUs, 1 GPU. This is the way you request GPUs on Thorny Flat. It would be the same on Dolly Sat. I will be using GPU inter just because I will get it quickly, and I think it was separated to give preference to inter for this workshop. So just to get it quickly, I put it there. And here I'm declaring what is the image, the singularity image that I will be using for training this model, and what is the Python script that contains the Python code for the training for the model. And I am just executing this summarily just to get an idea and put that which was the GPU that I got. So eventually later I can compare if I run with a P6000 and now I'm getting a different GPU, well, how fast it is. And this is the actual line for executing the Python code under this singularity container. And this is the important line here, put this --mv, so you activate the NVIDIA GPU card inside the container. This is all that you need to know for this. I have here, I think here, the example with me is a copy of all that. It's a copy of the submission script, the Python script, the data folder, and all that I have to do is execute batch this, and I will get that. I can monitor. This is something that all this with this learn, the submission script, we will see that in detail. This is just the particularity for GPUs, for deep learning. But if you want to understand better the submission scripts, how you monitor those things, feel free to attend tomorrow, same time, same Zoom link is in the introduction to HPC. We will go into all this user. So you see here, I have this is still running. I can actually do something else. Go into this machine and see in it. Oh, wow, it was so fast that it finished. It finished already. Okay, so now it's gone. Oh, wait. Okay. I need to check if I did something. Well, it will start producing this kind of message. The GPU that I got. Oh, close it. I have to. Okay, so let's review here. Okay, so the data is here. Another thing that happens, and this is very particular for this cluster, for Dolly, so most likely will be like that. Compute nodes, they do not have internet access, so you cannot download models or weights or things of that nature over internet from a compute node. You have to do it in advance. That's what I did. I download all the tiny images of the digits is in the data folder. So I am here recreating the test set and the training set from the data that is inside the data folder. They are taking all those images. Here I am taking all those and creating like a feeder. This is in PyTorch, something that will submit the elements as the model start digesting those for the processing. And here is the fitting function, written by hand. In some other engines, it could be automatic. It will happen without so much code. It could be make it smaller. This is just for showing more, for showing the validation, for showing more statistics about what is happening inside. And you run it here, and at the end you print the losses, all that. And here, this is in PyTorch, how you say the model. When it finishes, it will have that zip file there, and that's what I think we have now. So you see at the end, you have the model here stored in the zip file that contains the model, so all the structure, the architecture of the neural network, and all the weights. And later you can rebuild the model and start improving on that, or adding things. Some of the things that we do, or typically people do with that, is they take a very big neural network that has been produced by someone else, somewhere else, and they just adjust. They took all the weights, they just remove for the final portion of the neural network, the final layers, and they retrain the network just for adjust all the recognition purposes for something specialized, for something medical, for something in biology. They take the advantage of something, the big network that has been trained. All the filters, people assume that they are generic enough for capturing edges, for capturing curves, and they just need to improve or just train the final layers. That makes the model much simpler to train compared with full training of millions of elements. Let's say neural networks today, they have literally billions of weights, could have 10 billion, 20 billions of elements that you have to tune. So it's very expensive. Even for those high-end cars, it's unfeasible for those cars. And so other people in those big tech companies, they do that, and they release those models with the values, and you just use them for your own purposes. We reached noon, so with this we close the session for today for GPUs. Next week we will be mentioning a little bit about the session will be on molecular dynamics. This is a big chunk that's more specialized for some people. But this is another big reason why people use GPUs, are classical molecular dynamics, especially when you are dealing with biological chemistry. So those are proteins. Small protein have thousands of atoms. So the movement of all those things is computationally expensive, and GPUs play an important role on those. And we have also several engines, several packages that have been optimized for GPUs. That's one thing. Another thing are more generic stuff for example, for computational fluid dynamics and some other applications where GPUs play a role. So that will be next week. Tomorrow, for those of you who want to attend, it will be on a little bit on this Learn, submitting jobs, interactive jobs, non-interactive jobs, on a more general context for everybody, not in particular for GPU. So thank you very much, and we will see each other for tomorrow.